Hey, we're back to limits here, loving and learning and living those limits. So let's take a look. Today we're going to work on piecewise functions and move to when we don't have a graph to help us out. But as a warm-up, we've got this triple piecewise function here, and we've got the graph here to assist us so we can hopefully visualize these things that we could do algebraically. So the first limit is, what is the limit of this function as x approaches 5? Now certainly you can look at this graph here, and as x approaches 5, we are right here on the graph. Nothing special, it's just a normal point on the graph at 5, 7, so those y values are approaching 7. Let's just think about how we could do that if we didn't have this graph. Would I need to draw the whole graph just to do that? No. I would look at these restrictions here for each of these pieces and focus on the x value that you're talking about. We're talking about 5. 5 belongs to this restriction here. 5 is greater than 2. So you would be talking about on this graph, which is just a parabola. You should be able to recognize that. And since you're beyond the x value of 2, you're just smack right into that graph. Nothing special going on at 3, 4, 5, 6, 7, etc. So you plug 5 right into that. 5 minus 3, 2 squared is 4. 4 plus 3, 7. The limit as x approaches 0. So we've got this graph here. Take a look. When x is 0, hopefully you're feeling pretty comfortable with identifying these things pretty fast. And the y value is 2. Again, it's just a normal point on the graph, nothing special happening. If you didn't have this whole graph, you would be focused on the x value of 0 and paying attention to these restrictions, and 0 falls in this interval, so you would be using this middle piece, plugging 0 into there. 0 plus 2 is 2. Okay, now let's take a look at these two, because these are really where the piecewise functions can mess with you, but not a big deal at all. X approaching -1. Now -1 is right here on the x-axis, and you'll notice that from the left, the limit is approaching a y value of -3. On the right, the function is approaching a y value of 1. So the limit is 1 from the right, -3 from the left. That is our classic DNE does not exist. The left does not equal the right. Now, if I didn't have the graph in front of me for that, I would be focusing on the x value of -1. And here's where you definitely just got to watch out. -1 is what I call sort of a borderline x value for this piecewise function. It changes from this piece to this piece. Now this is where the closed circle would be on this graph, but when it's at that sort of transitional value, I want to make sure, does the left equal the right? And so this is a case where you'd have to check the limit from the left and the limit from the right just by essentially plugging -1 into each of these pieces and seeing if they give you the same y value. -1 into this will give you, -1 plus 3 is 2, 2 squared is 4, -4 plus 1 is -3. That's the -3 that you see there with a closed circle. But plugging -1 into here, -1 plus 2 is 1, and that would be with an open circle. 2 different y values means limit does not exist. Left and right doing 2 different things. Limit as x approaches 2. If you're looking at this graph, that's a very quick answer, hopefully. When x approaches 2, y value is 4 from the left and the right. Left and right agree. Hey, there we go. If you were approaching this purely from the equation, again, the x value of 2 is the sort of borderline or transitional value where it changes from this piece to this piece. So you've got to worry about that continuity, essentially plugging 2 into both. 2 plus 2 is 4, and when you plug 2 into this second part, 2 minus 3 is -1, but squared is 1, and 1 plus 3 is also 4. So from the left and the right, it's a value of 4. So the limit is 4. So the limit can exist at these borderline values, or it cannot exist. And we saw an example of each one. So hopefully you kind of visualize that. And if it's not one of these borderline values, if it's just one of these other values, like A and B were examples of, then you just find the correct interval and substitute it into that equation, assuming nothing weird is going on at that point. So now these will go pretty quickly, hopefully. We've got this sort of a piecewise function here represented the same, similar way. The limit of this as x approaches -2. Now -2 is the transitional x value between this piece and this piece. So this is the classic where you want to check, does the left equal the right? And if you want to be a little more formal with your notation, like your calc teacher next year might want you to be, when we approach -2 from the left, does that equal the limit of -2 from the right with those little superscripts there? But yes, it's essentially plugging this in. So 2 times -2 is -4 minus 5 on the left equation, and we get -9. On this side, the limit from the right is -2 squared is 4, and 4 minus 2 is 2. The limit from the left does not equal the limit from the right. That's your classic DNE, left does not equal right. So pretty easy, right? And that's where you'd be nodding your head. Yes, Mr. Murray, it's very easy. X approaches 3. 3 is the transitional value here, so you got to check the limit from the left and the right. So 3 from the left side of this expression is plugging 3 into there. 3 squared minus 4, 9 minus 4, 5. And the limit as x approaches 3 from the right would be plugging into this second piece. 3 plus 2 equals 5. We got the same value. That means the answer is 5. If the left and the right agree, then that's the answer. Okay, last one here, just to hopefully bring it on home and just see a few more examples, and just to make sure you feel comfortable with it. We've got a triple piecewise again, so always more intervals. Just be careful. The limit of this function as x approaches -3. -3 is a transitional x value, so I've got to check, is this piece connected to this piece? Do they have the same y value at -3? So the limit as we approach -3 from the left. And I'm trying to be good with my notation, trying to be formal here. -3 from the left would be plugging it into that piece, and that will be 9, -9 plus 5, -4. Checking the limit as x approaches -3 from the right would be plugging it into this piece. So -3 minus 2, absolute value of that, and then plus 1, so -5, absolute value 5, 5 plus 1, 6. These values are not the same, so the limit does not exist. Left and right do not agree. There we go. So even taking the time to write out all the notation, it's not a very long problem if you really know what you're looking for. If I were graphing these two, visually that would show me that this piece is not connected to this piece, so there's a discontinuity at -3. Part B, x approaching 4. 4 is the other borderline x value, so let's check it out here. The limit as x approaches 4 from the left would be absolute value of 4 minus 2 plus 1, and that would be 2 plus 1, 3. What's the limit as x approaches 4 from the right? We're plugging it into this piece now. Ooh, nice little trig action here. We get the secant of 4 times pi over 6, which is 4 pi over 6, and when you reduce that, that's 2 pi over 3, as you're used to seeing it. And the secant of 2 pi over 3, remember that is the reciprocal of cosine of 2 pi over 3. Cosine of 2 pi over 3 is -1/2 because it's quadrant 2. So the secant of that is -2, plus 5 is 3. So that alone, nice little trig review there. They agree, so that's your answer, 3. And lastly, the limit as x approaches -6. -6 is not a borderline transitional value. -6 belongs to this interval. It is less than -3. So it would just be a normal point on this parabola. Parabola has no sort of weird domain restrictions or holes or VAs or anything weird going on. So we'll just plug -6 into there, direct substitution, and we should be good. Just watch your order of operations. So you square that 36, make it negative, and then add 5. -31. All good in the hood, and there we go. All right. If you watch this all the way to the end, leave a comment about your favorite music group and get a bonus point. All right. See you later, kids.